Hello, phenomenal ladies and gentlemen. It's Matthew Faro here again, and welcome back to my space. Yeah, for the past few days, there has been a controversial chatter about a particular limit problem that I've decided to make more limit videos. Yeah, today we'll be looking at some limit shenanigans, limits involving infinity. So either infinite limits or limits at infinity. And in this video, I'll try to keep it as short as possible. If it is possible for me to finish the 6 questions in between 30 minutes, I'll do that. But if I cannot keep it on that 30 minutes, I'll break it into 2 videos. So let's get right into it without wasting much of our time. Okay. All right. So before we go too far, let's remind ourselves what the concept of limit is. Again, we know that when we ask for the limit of a particular function as x approaches a, we are asking basically for the output that the f of x is approaching as the input x is approaching a specific value a. So for us to say that limit of f of x as x approaches a is equal to L, it means that as we get closer and closer to a, either from the right or from the left of a as the input, the f of x itself is getting closer and closer to L. All right, so when we have the limit of x as x goes to infinity, so f of x in this case is x. So when x is 1, f of x is 1. When x is 2, f of x is 2. As we approach infinity, because the graph is just the diagonal graph, as x approaches infinity, we know that y will also approach infinity. So it's as simple as that. We know that that is infinity. And we have said that in most cases, when we want to evaluate limits, what we do is make direct substitution. And if that doesn't work, if we hit indeterminate forms, then we go through some other mathematical and logical manipulations, which include using factorization, algebraic simplification, rationalization, using trigonometric identities, and then at some higher level we talk about using L'Hopital's rule if it satisfies some certain conditions, and then using series expansion. All right, so that being said, we need to also understand that when we are talking about infinity, it is a very special concept. The fact that it is not a number, it needs to be treated with care. Okay, so first and foremost, we need to understand that when we say the limit as x goes to infinity of any rational function, it doesn't even have to be a rational function, any fraction such that as x goes to infinity, it blows up. It goes to infinity while the numerator either remains constant or goes slower to infinity. Then in this case, we have that the whole fraction will approach 0. So it's just a simple ideology. So when you consider f of x equals to 1 over x, for instance, so when x is equal to 1, this whole f of x will be 1 over 1, and that is 1. When x equals to 10, that will be 1 over 10, which is equal to 0.1. When x is equal to 100, you can imagine what is happening. We keep getting smaller and smaller, 0.01, and so on and so forth. And if x becomes larger and larger, we get 0.000000000, which is something that is getting closer and closer to 0. On the left hand side of 0 as well, so if you think about when x is -1, okay, when x is equal to -10, when x equals to -100, you just get negatives of these things. You get -1, -0.1, -0.0001. All of them are also approaching 0, either from the left or from the right. So it means that the limit of a over x, as x goes to infinity, a could be any number. So it could be 1, it could be 2, it could be any constant. So far, it is not going anywhere, while x runs faster to infinity, then the whole fraction will be equal to 0. Note that doesn't really mean that this is a over infinity equal to 0. We are not saying a divided by infinity is equal to 0. As a matter of fact, I'm not saying that the limit of x approaches infinity of 1 over x is equal to direct substitution 1 over infinity, which is equal to 0. No, that is not what I am saying. Okay, because infinity is not a number, so we cannot say 1 divided by infinity. How many times can infinity go in 1? That is not a reasonable question, because infinity is not a number. But we are saying that the function 1 over x, it is the one changing. So 1 over x when x is equal to 1, 1 over x when x is equal to 2, 1 over x when x is equal to 100, 1 over x when x is equal to 10,000, and so on and so forth. So as x is becoming larger, as x is becoming bigger, 1 over x as a function is going to 0. That is exactly what it means when we ask the limit question. Okay, so we don't have to do the mistake of saying the limit of 1 over x. So it's better for us to avoid writing out that it is 1 over infinity. We just know that limit of 1 over x as x approaches infinity is equal to 0. So that being said, we can actually say that the limit as x goes to infinity of x is infinity. So it means that as x is becoming larger and larger, x is becoming larger and larger. It's as simple as that. So as x goes to infinity, the limit goes to infinity. So then also, when we have the limit as x goes to infinity of any power function or any polynomial function, it follows the same ideology. So which means that if we have kx as a constant, or kx squared or kx cubed, then it means that we can bring out this k as a constant, the limit as x goes to infinity of x, and we've already said from item number 2 that this is infinity. So this is k times infinity. So infinity here is not saying it's a number, but we are looking at k times a possibly very huge number, and this is equal to infinity. So this is infinity. All right, so with that alone, we've seen the solution to the first question here, and we are saying that the limit as x goes to infinity of 4x is equal to 4 times the limit of x as x goes to infinity, which is just 4 times a very possibly big large number, which is equal to infinity. So this is a valid answer in limit. Remember that the legit answers in limit, we have the real numbers, positive, negative, zero, rational or irrational. All these are valid answers. Then 2, we have positive infinity or negative infinity. Then we can also have the case where the limits actually do not exist. Okay, so this is a correct answer. So anytime we have a polynomial, a single monomial, or a series of monomials put together to form a polynomial, then we know that, so in general, again, for the limit as x goes to infinity of ax squared, which is a times the limit as x goes to infinity, maybe I should use n generally, of x raised to power n, is, and since limit pass power, this is the limit as x goes to infinity of x raised to power n. That is a times infinity raised to power n, which is all together infinity. There is no problem with infinity being multiplied by itself. Where it becomes a problem is when you have infinity minus infinity or infinity divided by infinity. These are indeterminate forms. So we can add up infinity, we can multiply infinities. So where there's a problem is when we subtract or we divide. All right, so that being said, the next point of call is number 2. So with what I have mentioned here, we can now look at what is happening with the second question. So copy and paste. In this case, it's a polynomial, but if we attempt to put in infinity directly, we have 16 times infinity minus 3 times infinity, which is infinity minus infinity. We do not want this. This is an indeterminate form. Okay, actually there is a way we could have seen the answer to this, thinking about dominant behaviors of a function. So when you look at 16x squared minus 3x, this 16x squared is the dominant term. Dominant because it goes to infinity faster than 3x. So what is the hierarchy of dominance? We have natural log of x is, grows very slower than square root of x, which goes very slower than x, which goes slower than any positive power of x, and this grows slower than exponential functions, and this grows slower than factorials. Okay, so this will be slower than x factorial, and this grows slower than x raised to power x. So when you have a lineup of terms in a particular expression, and you are considering the limit of that function as x goes to infinity, if any of them contains x raised to power x, then that is going to be the dominant term. So you can ignore all the other terms of the expression. So in this case, since I have x squared, coming from here, and I have x coming from here, then I know that this grows faster. So I can actually avoid. So this question is the same thing as looking at just 16x squared, because it is what happens at 16x squared that will determine what happens at 16x squared minus 3x. That is the meaning of dominance. So in this case, just as we have in this item here, so this is just going to be infinity. However, if we want to be technical about it and not talk about dominant term, the common trick that we use for questions like this, limit as x goes to infinity of 16x squared minus 3x, is to factor out what we perceive as the dominant power of x. So this is going to be the limit as x goes to infinity. So x squared is, dominates x. So we have x squared into bracket 16 minus, and when you factor out x squared from 3x, you are left with 3 over x. Why are we doing this? We want to be able to separate, put one single term, we want to factor it into product of two terms, and then use what we have here. Okay, so the limit, we know that the limit of a number over x, or any power of x even, will give us 0. So with that, we can say this is equal to the limit as x goes to infinity of x squared times the limit as x goes to infinity of 16 minus 3 over x. So the first one here is infinity, and the second one, so the limit as x goes to infinity of 16 is just 16, and the limit as x goes to infinity of 3 over x is 0. So we have infinity times 16 minus 0, and infinity times any number, is infinity. So anything that goes to infinity multiplied by anything that goes to a constant number definitely give us infinity. So that ascertains what we already know from the dominant case. Then the third question here, we have the limit of the square root of 16x squared minus 3x. So it's almost a similar trick that we pull here. It's just that the fact that this one has square root might be a little bit tricky, but all is still under control. So when we have this, so generally we know what the term under the square root goes to as x goes to infinity. We've already seen that in the previous question. We know it goes to infinity. So this is basically saying what is happening to square root of x as x goes to infinity. So this guy goes to infinity as well, even though it grows slower while it's on its way to infinity. Because in fact, when you look at the graph of square root of x, which looks like this, so as x goes to infinity, this guy, even though it's going slowly, it is also going to infinity. So it's no problem to find the square root of, in quotes, find the square root of infinity. Again, like I said, where the problem is subtracting infinity from infinity or dividing infinity by infinity. So in this case, I could simply just say, all right, this is the limit as x goes to infinity, and using the same trick as before, underneath the square root, I factor out x squared, and I will have 16 minus 3 over x. Then we know from the laws of surds, radicals, that square root of ab is equal to square root of a times square root of b. So it means I can split this into the limit as x goes to infinity of square root of x squared times the square root of 16 minus 3 over x. But what is square root of x squared? So the first thing that will come to your mind, as we've learned from elementary school, is just to say square roots cancel square. However, at this level of mathematics, we should know that this is not just square cancel square root. This is absolute value of x. And what does it mean? We know that absolute value of x is equal to, it is x if x is non-negative, that is, if x is non-negative, and it is either 0 or positive, then it is negative of x, which makes it positive if x was originally negative. What am I saying? If I have absolute value of 2, that is just going to be 2. I will not do anything to 2, because the primary objective of absolute value is to make something positive. So if it is already positive, it does nothing else. But if it is negative, according to the formula here, we multiply it by a negative sign. So negative times negative 3 will give us 3. The mission is completed to make it positive. So how does this apply to square root of x squared? Because this is simply, so when you look at square root of minus 2 squared, the square root function is a positive function, as you've seen with this graph. This is the graph of the domain and the range. They are, from 0 to infinity. So when you look at this square root of negative 2 square, we cannot do square root cancel square, because that will give us negative 2. But we already know that the range of the square root function is positive, so it is not possible for us to get a negative answer for the square root of that. And we know that this is square root of 4, and the square root of 4 is definitely 2. So also, a common mistake that people make, square root of 4 is not equal to plus or minus 2. There's a difference between asking you for the square root of 4 and asking you to solve the equation x squared is equal to 4. So if I say x squared is equal to 4, and I'm asking for what you solve the equation for value of x, I know that the square function itself, the square function, okay, has the domain to span across and the entire real number. So it includes the negative numbers and the positive numbers. So we could have the negative numbers involved to square to give us 4. And that is why we usually say, okay, then x will be this plus or minus whatever the square root of 4 is. So square root of 4 in itself is always positive. The square root of anything is a positive function. So I can say it is a non-negative function because it's either positive or 0, especially at this level of calculus. Okay, so when you get to complex stuff, complex analysis, or calculus of complex numbers, then okay, we can now start talking about the different branches that the square root function or root function in general could have. But with real numbers, real calculus of real variables, the square root function is a non-negative function. Okay, so that being said, so we've established the fact that the square root of x squared is absolute value of x, not just x. So that is very important and vital to this in this question. So we say this is absolute value of x, and this is the limit as x approaches infinity of the square root of 16 minus 3 over x. And because x is approaching infinity, the kind of numbers that we are going to have, they are positive. So x is a positive number. So it means that absolute value of x is going to be x. So I can write this as the limit as x goes to infinity of x times the 1 and the square root. So times the limit as x goes to infinity of the square root of 16 minus 3 over x. And we already know that limit pass power, so it's also pass root. So I can rewrite this as the square root of the limit as x approaches infinity of 16 minus 3 over x. So this is going to be infinity times the square root of 16 minus 0, because the limit of 16 is 16, irrespective of what you have. And that is infinity times 4, which is just going to be infinity. So this is the general trick we use, factor out stuff, then especially the highest power, then move on. So if it involves square root or an even root of a power, then if it is not odd, you can be sure that the absolute value will show up. So this is number 3. The answer is infinity. We are slowly building up to the controversy that I talked about at the beginning of the video. So the next question on the list, number 4, copy. All right, so we have this. Again, if we think of it as, substituting infinity directly in quote again, because infinity is not a number. We've already seen, that is why I built it up nicely this way. We've already seen from number 1 that the limit as s goes to infinity of this is infinity. And the limit from number 3, we've seen that the limit of this is also infinity. So we know, because this is limit as x goes to infinity of 4x minus the limit as x goes to infinity of square root of 16x squared minus 3x. So we've seen in number 1 that this is infinity. We've seen in number 3 that this is infinity. This is an indeterminate form. So it means we need to do something. Generally, when we have indeterminate forms and we cannot just factor out stuff, okay, if we cannot just factor out stuff, then, because of course we really cannot factor these things out like this. So what we do is rationalization. We turn on rationalization. All right, and in this case we rationalize, because this is we can see this as a fraction. Every number is a fraction. Every real number is also a rational number. Oh, sorry, that's a wrong statement. So every rational number is a real number. So every integer, I'm supposed to say that, is a rational number. So this is equal to the limit as x goes to infinity of 4x minus square root of 16x squared minus 3x over, so we want to do times 4x plus square root of 16x squared minus 3x all over 4x plus square root of 16x squared minus 3x. And we know that by difference of 2 squares, the numerator becomes 4x squared minus, so this gives us 16x squared minus 3x, because square root of a and square root of a is just a. So technically we should say absolute value of a, but in cases like this, it's just a. So all over this 4x plus square root of 16x squared minus 3x. So anytime we do stuff like this, it helps us get rid of the infinity minus infinity. That is only in a case where we cannot factor out like this to solve the case. Okay. All right. So in this case, we now have this to be the limit as x goes to infinity of 16x squared minus 16x squared plus 3x all over 4x plus, you remember that we've done this before, the exact trick we did here, so I'm going to just bring it in. This is absolute value of x times square root of 16 minus 3 over x. So I'm using the exact same thing that we did here I'm bringing it down here. I don't want to waste time by going over it again. So 16x squared cancels 16x squared. And this is equal to the limit as x goes to infinity of 3x over, so you remember what we said the last time, as x goes to infinity, absolute value of x is just going to be x, because that's to be positive values of x. So we have 4x plus x, then square root of 16 minus 3 over x. Then if we factor out x in the denominator, this is the limit of 3x all over x into bracket 4 plus the square root of 16 minus 3 over x as x approaches infinity. So x here cancel out, and this is equal to the limit as x goes to infinity of 3 over 4 plus square root of 16 minus 3 over x. The limit of 3 is just 3. The limit of 4 is just 4. The square root of the limit of 16 is just 16. And the limit of 3 over x as x approaches infinity is 0. We've seen that over and over today. So this is 3 over 4 plus 4. And this is 3 over 8. So the video is already 30 minutes long. So I'm going to stop it here for now. Then when we come back in the next video, we're going to see how it differs from these other two questions where they are almost the same thing, but this one is positive, is plus, unlike number 4 where we have negative. And this one is also plus, but this time around x approaches negative infinity. So till we see you in the next video, stay cool and enjoy mathematics. Bye.